Hello, welcome to the second video from chapter 19. This video is going to focus on calorimetry. And so what we mean by this word is how Q relates to T, how heat relates to temperature. So we're going to get into some equations relating to this, how Q relates to T. So I'll summarize some, I'll give an overview of, so this section we're mainly going to focus on solids and liquids. And we'll hold off on talking about gases, and I'll discuss a little bit more in depth on why that's the case in just a second. So by the end of this video, we should be able to answer problems on calorimetry. And this is a very typical style of problem right here. How much ice, and we're going to say that the ice is initially near its melting point. So how much ice at 0 degrees C would it take to cool down half a liter of water at room temperature, 20 degrees C, to a final temperature of 5.0 degrees C. And so we'll need to know these two constants in order to solve this problem. So we'll get to that towards the end of the video. Okay, so first of all, I just want to mention that, so I want to remind everyone of the first law of thermodynamics, and that is delta E thermal is equal to Q plus W. Now, I said that solids and liquids are very different than gases, and so I want to quickly sum up why this is. So for solids and liquids, it's true that these are very hard to compress. So solids and liquids basically don't change their volume. So they don't. It's hard to change the volume of these things. And as a result of this, the work done either by the system or on the system is equal to 0. And so because of this, the change in thermal energy is equal to the heat supplied by the surroundings on the system. And this is what we're going to study in this video. So this video is going to precisely talk about the relationship between Q and delta T. And the reason it's so easy for solids and liquids is that we can have this assumption, or it's a really good assumption to say that W is equal to 0. So if we were to draw PV diagrams for solids and liquids, they would always be vertical lines. Always, right? That change in volume is going to be 0, basically, for those. Gases, though, it's very different because W is non-zero. So I just want to remind you that E thermal was something that's closely related to delta T. So delta E thermal is equal to something times delta T, and we're going to see what to fill in here towards the end of chapter 19 and in chapter 20. Q, though, we have no idea what to write here for Q. And Q really here depends on the path. Depends on path. It's a path-dependent quantity. And by path, I mean a path in the PV diagram, the path on the PV diagram. So because of this is a lot more complicated. And so we're not going to be able to answer this question until, so we're going to do a whole video just on section 19.7 that'll help us answer this. And we're going to expand on this in chapter 20. So another video summing up the important parts of chapter 20, where we see the microscopic origins of some of the concepts that we're going to see in 19.7. So basically, to talk about gases, to talk about what we're going to do in this video, we're going to need 2 different videos to talk about what goes on in gases because it's more complicated. But like I said, this video we're gonna focus on just solids and liquids because delta E thermal and Q are the same thing. So calorimetry, which is the relationship between Q and delta T, is going to be very easy as a result of this. Okay, so this is a picture from a previous video, the video on thermal expansion and phase changes. So I just grabbed that video right here, or grabbed this picture from that. And I want to focus, so we can label the steps on this diagram. So there are 3 steps where the temperature is increasing. Well, let's just do these in order. So 1, 2, 3, 4, 5. Okay, so we're going to have a different formula describing heats delivered during each of these pieces. So steps 1, 3, and 5. These are processes where you can change the temperature. So the temperature can change, and there's going to be one equation relevant for this. So looking at the book over here on the left, see how it has Q equals something for a temperature change, and then later on it talks about phase changes, and then it gives a different formula for Q. So these two different formulas for Q have to do with the two different stages you can be in this figure. So for steps 1, 3, and 5, we have a relationship between Q, the heat added, the total heat added, and the total temperature change. So notice these are lines, these are straight lines, and so it's a proportionality. So the amount of heat that you add, and by the way, Q, it's understood that it's a heat transfer. We don't write delta Q, but it's understood that it's a change in energy in the form of heat. So some books you might see a delta Q, but really it's customary, and in your book follows this custom that we don't write the delta for Q. See how, like, for the first law right here, delta E, we don't write delta Q and delta W. It's understood that those are already those are energy transfers. So I'll talk more about this equation in just a second. I also want to quickly mention what the relevant equation is for steps 2 and 4. So remember that steps 2 and 4 are phase changes. And for the phase change, there's no change in temperature. So it wouldn't make sense to write down an equation where we have a delta T for steps 2 and 4. They occur at a particular temperature, but the temperature isn't changing. It does require a certain amount of heat to change the phase. And remember, in this video, heat and energy and the overall change in energy are the same thing because there's no work. So Q, it's going to depend on how much stuff you have, right? If we have twice as much ice, it's going to take twice as much energy to melt that ice. So it makes sense that it's proportional to mass. And then other than that, though, it's just some constant that depends on the particular phase change. So you might see these equations with various subscripts. So like right here, you might see a F or a V. And that has to do with the latent heat. Well, I'll talk more about this equation later on, but let's first focus on steps 1, 3, and 5 first. Okay, so Q equals mc delta T. So first of all, just to define these things. So m is mass. Probably guessed that one. Delta T is change in temperature. Change in temperature. Again, you could probably guess that one. So C is a constant that tells you how much energy does it take for a given amount of mass and a given temperature difference. So the C is going to be some number, and the SI units will be joules because we're going to be left over with a energy, right? The units for Q are energy. So joules divided by, and then grams or kilograms. So I guess for the SI unit, you would want kilograms here, times Kelvin on the denominator. So what this number is right here is if you have 1 kilogram of that amount of material and you want to heat it up 1 Kelvin, how much energy does that take? Okay, and this is called the specific heat. So when we talk, you'll notice in this equation it's exactly the same thing on the left here for the book. Q equals mc delta T. Your book then mentions, it says, oh, by the way, you can write this not in terms of mass, but in terms of moles. So notice how this equation right here, Q equals n capital C delta T. It's the same equation, except now instead of talking about mass, we're talking about moles. So when we switch over to gases in later videos, we're going to use a very similar looking equation, except it's going to be n times capital C times delta T. So that capital C will also be a specific heat, but it's per mole. The units of that will be per mole rather than per gram or per kilogram. So your book says that that's the molar specific heat. So if someone just says specific heat or massive specific heat by mass, they're referring to this formula. And for solids and liquids, this one's more useful. When we talk about gases, we'll use the other one. So I won't write down the other one right now. We're going to see it plenty in future videos. Okay, so this constant here, specific heat, it depends on not only what substance you have, like H2O right here, but it also depends on what phase it's in. So notice how the slopes for step 1, step 3, and step 5 don't have to be the same. It doesn't have to take the same amount of energy to heat up ice by 1 Kelvin as it does water by 1 Kelvin or steam by 1 Kelvin. So if you take a look at this table right here, it shows that for water, so the very last row of this table, for water it gives a value, so this lowercase c is the one by mass, and it's 4,190. So C for water is 4,190 joules per kilogram Kelvin. The way I remember this number is, so 4.19 is for some reason easier to remember in my head. And it's 4.19 if you write it two different ways. So you could write kilojoules and kilograms on the top and the bottom. Or if you multiply both sides, or I guess, multiply both the numerator and the denominator by 1,000, you can also write this as 4.19 joules per gram Kelvin. So notice how if you either have kilo on both the top and the bottom, or you don't have kilo on both the top and the bottom, the number is 4.19. It's just this 4190 if you have joules on the top and kilograms on the bottom. So a kilo on the bottom and not a kilo on the top. So for me, it's easier to remember, it's just either of these two. So either keep both kilo or both not have kilo and just remember the number 4.19. The original point I was making, though, was that, so see how water and ice have two different numbers? So ice doesn't require as much heat to get the same temperature difference. So see how on this diagram, I accidentally did this correctly. So notice how ice is gaining temperature at a greater rate. So notice how for a given Q difference right here, the ice, in step 1 right there, the ice is gaining temperature, a lot of temperature difference right here, but the water doesn't gain as much for the same heat added. The water doesn't gain as much temperature right there. And steam would even have a more drastic horizontal line right here. It doesn't gain temperature very quickly at all because the specific heat for steam is so large. They don't include it on this table, but you can find it elsewhere. Okay, so that's the first equation. The second equation I want to focus on, and really this is just going over some terminology here, is this Q equals for phase changes. We have Q equals mL. So this L is called the latent heat. And it could be, so the latent heat of vaporization for one kind of phase change, or the latent heat of fusion for another kind of phase change. So notice how I remember, I've already written these words. See in black on the diagram, in quotes, I write fusion right here and vaporization on right here. So no matter whether you're going to the right or to the left on this diagram, whether you're freezing or melting, we call it fusion. And there's a certain number associated with that, depending on how much energy it takes to do that phase change. And that constant, which, by the way, it's going to be in joules per kilogram for SI units, that'll tell you how much you need. And so there should be another table in the book right here. Right here. So this LF is the latent heat of fusion. So it's talking about the melting or freezing, and then the LV is the latent heat of vaporization, which is talking about the water, the liquid gas boundary. So by the way, there is a latent heat of sublimation. If your material, if substance sublimates at a certain pressure. So for carbon dioxide, if you're looking at the value at 1 atm, they would have a latent heat of sublimation. So you might see a capital L with a subscript S on it. And this is really, it's just these two equations, along with conservation of energy, that dominates these two sections. So calorimetry is just the practical application of these two equations to a problem. That's what we're going to look at for this problem right here. So calorimetry, and the idea is right here. When you mix things, so here we're going to mix water and ice, whatever energy is lost by the water is gained by the ice. As long as these are that's the only way that the energy is exchanging. So we're going to use that fact to help us solve for the final temperature. So that fact along with these two equations. Okay, so back to the original problem. So the original problem right here. So the way you normally want to set up calorimetry problems is that the Q for the ice going to 5-degree water, call it 5-degree H2O. So this is just focusing on the ice cube. This is how much heat is delivered to the ice cube. And this is how much heat is going to be delivered to the 20-degree water going to 5-degree water. So in equilibrium, I mean, when the ice heats up and when the water cools off, this energy exchange is going to keep happening until the two become equal in temperature, until they're both 5 degrees and water. So because the energy flow is exactly like this, these two are going to sum to 0. So one of them is positive and one of them is negative, and they're equal in magnitude. And that's exactly what your book is saying right here. They're equal in magnitude. So as for which one is which, well, which one has heat delivered to the substance? To heat up the ice, Q must be positive. So this one should be a positive heat, and this one should be a negative heat. So we have to make sure that whatever equation we write down satisfies that. Okay, so we know everything except for the mass of ice. Remember, the original problem asked for the mass of ice required for this. So M ice is going to be our unknown. Every other thing that I write down here is going to be a parameter where we already know the number here. So this ice is undergoing two things. It's undergoing a melting. So that ice needs to melt and become water. So the energy required for that is M times L, the mass, however much ice that is, and then this is the number that we can plug in. And then we also need to heat up that now water. The ice cube is now melted to water. And it's going to be M times C water times delta T. And that delta T is going to be T final, 5 degrees C minus T initial. So notice how both of these pieces are positive. So this piece and this piece are both separately positive, because during both of these steps, the ice melting and that 0-degree water heating up to 5 degrees, both require heat being delivered to the system. And then the next piece is going to be, well, how much water did we have? It was 500 milliliters, half a liter, and the density of water is 1 kilogram per liter. So half a liter means half a kilogram. So this right here is going to be 500 grams of water. So again, we're using the MC, C for water, times delta T. And delta T is going to be, it's the final minus the initial temperatures. So it's MC delta T for the cooling. And those two terms sum to 0. And indeed, this first term is positive, and the second term, see how 5 minus 20 is negative 15 degrees C, is negative. So if we plug in the specific heat for water is 4.19 joules per gram Kelvin, or gram degree C. It doesn't matter because it's a temperature change, remember. And plug in the latent heat of fusion is 333 joules per gram degree C. Oh, sorry, remember, no temperature change. This is just joules per gram. We can solve for m ice. So plugging this into a calculator here. Oops. Looks like I get 88.8 that'll be grams of ice. So we had to start off with this much ice in order to get our system to 5 degrees C at the end. Okay.